Hello, everyone. My name is Joe Barco, and I'm Senior Director of Marketing at Unchained Labs. I'll be your moderator, and thank you for joining us today. We'll have a Q&A session at the end of the presentation. To ask questions, all you have to do is click on the Q&A box in the Zoom navigation bar to either the top or bottom of your screen and type your question. We'll get to as many of them as we can. And now I'd like to introduce Rick Sidler, our Senior Field Automation Scientist. Today, Rick will discuss an automation-based approach to reagent screening and how that may lead to finding better reaction conditions faster, with less hands-on time and lower cost. Now I hand it over to Rick.
Thanks very much, Joe, and welcome everyone to the webinar today on reaction screening. In 1977, NASA launched two spacecrafts, Voyager 1 and Voyager 2, only 16 days apart. The goal of these spacecrafts was to explore Jupiter and Saturn. Today, 43 years later, those two spacecraft are still going. And in fact, in 2012, Voyager 1 crossed out of our solar system and into interstellar space, followed by Voyager 2 in 2018. Although they're still our neighbors as far as the cosmic space goes, they're so far away now that it takes light or radio signals about 20 hours to travel one way between us. On their current trajectory, these two spacecrafts will pass by some of our nearest neighboring stars in about 40,000 years. So the corollary to you are here might well be that there's a lot of unexplored space around. Maybe sometimes you feel that way in your research experiences and projects as well, where you have a project and you're surrounded by a lot of unexplored reaction space, and you're not quite sure how to proceed or how to get all of the answers that you need in a reasonable amount of time. The good thing is that reaction optimization or reaction screening through automation can help. So what are we going to talk about today? We're going to talk about reaction screening and screening sort of versus optimization. What do we mean? In reaction screening, we're typically looking at a number of discrete variables, things like unique catalysts or different ligands in a variety of unique solvent systems with different additives, acids or bases or other materials in a reaction, and looking at how the combinations of those materials affect the reaction progress or the reaction yields. Generally, we go into these reactions expecting that the majority of them are going to fail. And due to the number of variables that we need to look at and the factorial nature of these designs of experiments, where we have to look at every possible combination, there are quite a few reactions to run. We're typically talking in the hundreds or thousands of reactions with a relatively small set of reaction variables. So we expect the majority of these reactions to fail, but we go into the process with the hope or expectation that at least if we've designed our experimental space correctly, a few of the reactions will be successful, and that we'll now understand some reaction condition combinations that allow the reactions to proceed, and we can take those conditions on into reaction optimization. We're really not going to talk about reaction optimization really at all or very much today through this talk. We're really going to focus on the reaction screening portion. Well, why might we want to automate reaction screening? You know, it's a fact of life today in the current world and situation that the amount of time that we can spend in the lab these days is limited, and it's very precious. And to go into the lab to spend a lot of time doing a traditional approach that's very labor and time consuming, to run a few chemical reactions and have to track those reactions, create the analysis plates, do analysis of those reactions, is not very efficient. We can contrast that with an array-based approach, which we can perform using lab automation or robotics, where we can prepare hundreds of reactions and execute them simultaneously. We can run these on a smaller scale, being more efficient with our uses of reagents and materials. And more importantly, oftentimes we can get these results all at the same time so that we can make a better decision based on the results of numerous experiments rather than just a few. So what type of reaction space are we talking about here for screening? We're talking about relatively small reactions, individual reaction tubes of less than a milliliter in scale in a high density like a 96-well array. We could be looking at plastic disposable plates for reactions, or high throughput experimentation in salt and polymorph screening. Quite often in reaction space, we'll be looking at pressure reactions. So we might be looking at a high density set of experiments for hydrogenations or carbonylation reactions. Or we might be talking about reactions run in our insert reactors in the OSR. Where might we apply these reaction screening conditions? It could be in a diverse set of fields. It could be in polyolefin research, where we're looking at catalysts and co-catalysts and monomer, co-monomer mixtures for making plastics or various polymer materials. It could be in the pharma industry, where we're looking at either small molecule API creation, or we're looking at screening for conditions for production of biologics. And hopefully we'll be successful at coming up with a vaccine for this soon, for COVID. It could be in the area of agrochemicals, looking at crop protection and making materials that will better secure our food supply. Could also be in the fields of material science, such as creating new electrolytes for batteries to power our cell phones, our laptops, and our automobiles. Or it could be in renewable energy sources, where we're looking at new thin films or films for things such as solar cells. If you really think about this diverse set of fields, though, and you can really distill the requirements down to a few common things. First is the ability to create a set of reaction mixtures by accurately dispensing solids, liquids, and gases to prepare those mixtures for reaction. Processing those mixtures by heating or cooling with precise temperature control, and mixing so that we can allow those reactions to progress. And then finally, doing some sort of an analysis on those results. It could be sample preparation for offline analytics like GC or LC or other techniques, or it could be some sort of an online automated analysis as well. Whatever the process is that you're looking at, Unchained Labs is up for it. Whether it be a fully automated process requiring a lot of different capabilities linked together, a more focused workflow where we're only taking a piece of the workflow puzzle that's causing problems in your labs at the moment and automating that, or the preparation of reactions and screening them in individual reactors. These systems can be configured specifically for your applications. We have a collection or suite of modules that we can assemble in a variety of different configurations to support different chemical research needs on our Big Kahuna or a junior platform, and a variety of standard ARM elements as well. We also have the ability to do custom development projects where if something doesn't exist and you really need it for your research, we can create custom features and functions as well. Well, it really wouldn't do much good for us to provide you with automated techniques for setting up and executing a lot of different reactions if there wasn't some way to create the set of experiments that you wanted to analyze, and then to analyze the results of those experiments in an automated fashion. Because all that would do really is to move the block. Well, fortunately, we have a software suite called LEA for Lab Execution and Analysis that really brings it all together. The design of the experiment, the execution on the lab automation platforms, and the reporting of the subsequent results. And this software is really highlighted by three components. Library Studio, where we do our experimental planning, and it's a user-friendly, intuitive interface where you drag and drop materials and chemicals to define what you want to have happen in each well of an experimental design. This is then read seamlessly into a component called Automation Studio, which is responsible for control of the robotics platform to actually make the design or your recipe that you've created in Library Studio execute without the need for you to do any programming on the robot whatsoever. Automation Studio can also be used to control integrated third-party instruments or analytic tools as well. All of the results of these from the contextual information in the Library Studio design about the reagents, the relative amounts of those materials, the heating temperatures and stirring, all get stored into a common database. Likewise, any information generated by Automation Studio and the automated portions of the workflow are captured into that database as well. So these could be things like actual amounts of solid dispense. It could be timestamps for when each action occurs, when samples are taken for analysis, or it could be the actual integrated analyses as well. All of that data can be pulled into a common database or repository so that we can use tools like Polyview or Leah Analysis for Excel to search that data, collate it, and view and generate reports. So how does Leah run the lab? Scientists at their desk could set up a set of experiments that they wanted to design. That design gets saved into a database where it can be pulled up by the lab automation equipment and executed. As we mentioned, any of the results that come out of that automated experimentation can go back into the database, along with any of the integrated analytics as well, so that the scientist, again, can query and report on the results of those experiments. So Leah Analysis Leah is really designed to bring it all together, from the conceptual information about the design of the experiment and what goes into each one of the wells, to the analytic data or information about results, yields, conversions, and even chromatographic data or other types of information into the database. We mentioned earlier on that we have to run these screening experiments with this discrete set of variables because we don't really have a good way at the moment to predict which ones are going to be successful and which ones are not. Hopefully that's in the process of changing. Over the past few years, there's been quite a bit of interest in the fields of machine learning and artificial intelligence. These fields are really data-hungry fields. They need a lot of information to be able to generate predictions about reactions. And fortunately, the types of information that we can create using the Leah software and the automation equipment are precisely what's needed to help with automated modeling and predicting experiments. So we can create a set of designs and have all of that information in a structured form in a database. Likewise, all of the information about how the experiments were run. And very importantly, that all of those experiments are run in the same way so that there's consistency from experiment to experiment on the automation platform. The robot doesn't care if it's Monday morning at 8 a.m., if it's Friday afternoon at 6 p.m., or if it's 2 o'clock on a Wednesday morning, it's happy to do what you've programmed it to do. All of this data then can be searched and output as structured information in a format that can be used for modeling and prediction experiments. We've seen over the last couple of years a number of presentations and publications now starting to come out of our customer base describing the use of these workflows in automated machine learning and artificial intelligence areas. And just some highlights here. Recently, Amgen talked about combining automation and data-driven modeling. Out of the BMS group, a presentation on automated reaction development. Sanofi Pasteur has talked about automated data analysis and reporting and formulation screening. And DOE experimentation continues to be a very useful technique, as reported recently by the group at GSK. We've also had a number of presentations recently. Most recently, just last month, Unchained Labs hosted a virtual Asia Pacific automation workshop where the two speakers, Jay Stevens from Bristol Myers Squibb, spoke about applications of lab automations to assembly of data sets for machine learning. And Akira Yada from the AIST talked about predictive models for catalytic reactions in artificial intelligence. In case you missed those, contact us on our webpage, and we'll be happy to share these presentations with you. One of the best features that I enjoy most about Unchained Labs is the user community and how willing they are to talk about their research and research applications and to publish and to share the results of these so everyone in the scientific community can learn from their experiences. So what I want to do today is just talk briefly about one particular case study around reaction screening. And that case study was actually published last year by Stephen Newman and associates at the University of Ottawa. And it was about exploring homogeneous conditions for the Buchwald-Hartwig amination for batch and flow chemistry. The Buchwald-Hartwig amination is a very common reaction in organic synthesis. It's used to couple aryl halides with amines to give aminated products. There are a couple of challenges, though, around these reactions. Most commonly, the reactions use strong organic or inorganic bases, and these materials limit tolerance of various functional groups. Or they use insoluble inorganic bases or conjugate acids that tend to plug flow reactors when you want to do flow chemistry research. There are a few examples of soluble bases such as DBU being used, but these were requiring expensive ligands to get them to perform well. So in this particular publication, they were looking at finding lower cost ligands that could extend the use of soluble bases such as DBU to flow reactor systems. So remember earlier on, we talked about the number of possible combinations and how that can really expand the number of reactions that you need to run in reaction screening. So in this particular paper, they were looking at 4 different nucleophiles in the chemistry, coupling those with 6 different aryl halides, using only 10 different ligands and 2 solvents. And to keep the number of reactions at a moderate level, they fixed the base as only looking at DBU and a single palladium source, concentration and temperature, and an endpoint assay time of 18 hours. The combination of these reaction conditions requires 480 experiments. That's 5 96-well plates to execute. The researchers executed these 480 experiments using a big kahuna system, and they identified 35 unique hits from those. The bar was really pretty low. A hit here was just identified as anything where they could see product produced by GC mass spec. And then selected of these reactions were further optimized, looking at different palladium sources and loadings, different ligand loadings, the variations in solvent and reaction concentration as well. And just to highlight a few of the results they found on the lower right-hand portion, we see the standard reaction conditions here that were used for screening. And just a few of the selected hits that they observed, looking at the coupling of this aryl bromide with this amine. In screening, when the halide is the bromide, they got 83%, but when it was chloride, only 20% yield. And this was using a xanthphos ligand. After optimization, still with the xanthphos ligand, but with a different palladium source, they were able to get the conversion for either of these aryl halide starting materials up to 87%. Likewise, coupling this aryl bromide with benzylamine, the HTE hit using xanthphos only gave a 20% yield of this material, where after optimization, the yield was raised up to 75% yield. And really strikingly, this aryl triflate with aniline, the HTE hit showed only a very small trace of material in the product of the reaction, but after optimization, that yield is now up to 85% yield. Not only were they able to show that they could use a less expensive ligand and get some very good reaction yields, by changing the base to DBU, which is a much more milder base, they were able to show that the reactions worked even in the presence of enolizable ketones or enolizable stereocenters. So it really expanded the scope of this chemistry available to all. Well, part of the reason for this screening was that they really wanted to be able to expand the chemistry to be able to perform Buchwald-Hartwig emanations in flow reactors. And so by using these soluble bases, they were able then to get these reactions to work in flow reactors, and also to expand it beyond just Buchwald-Hartwig coupling reactions, but also to include Mizuroki, Heck, and Sonegashira couplings. So the new reaction conditions really solved a couple of questions. DBU tolerates sensitive functionality under the reaction conditions. They identified lower cost ligands that allow this base to be used and optimize some of those reaction conditions. They've shown that the soluble base and conjugate acid enable the ability of these reactions to be performed in flow chemistry. And finally, they've demonstrated this on both batch screening and optimization and how it really applies to flow chemistry applications. Unchained Labs is proud to have over 300 customers in our customer base worldwide. We have a sales and support organization that can support these workflows worldwide. And we would be happy to talk to you about any needs in the reaction screening space. So finally, I have just one last question for you as we close this portion of the webinar, and that's which space would you rather be in, without automation or with automation? Thank you very much.
Thank you, Rick, for your taking us through your presentation on automation screening and the case study especially. We have some great questions that have come in while you've been talking. You still have, if you're in the audience, you can still ask a question using the Q&A box on the Zoom navigation bar. So Rick, first question is, you mentioned something about an OSR, and can you talk a little bit more about what that's used for?
Sure, the OSR is our automation sampling reactor. It's a deck element that comprises 6 individual reactors. Those individual reactors have independent temperature and pressure control and can run reactions from -20 degrees up to 180 degrees, pressures up to 400 psi. It's really a unique reactor in that it has the ability to sample into or out of the reactions while they're under temperature and pressure. We have, for reaction screening, we have an insert that will allow us to run reactions as low as about 650 microliters with sampling. And without that insert in, we can run reaction scales all the way up to about 25 or 30 milliliters.
Okay, thanks. And I think you're going to be talking more about that in a couple of weeks, I assume, at the next presentation.
Yep, absolutely. The next webinar in this series will be about reaction optimization, and we're planning to highlight the OSR there. So please join us for that if you haven't already registered.
It's September 1st, we'll just do a small plug. Okay. And then how can people get access to the other presentations on machine learning that you showed in the presentation?
Oh, yeah. Great question. So contact us on the website, unchainedlabs.com, and go to the contact tab there, and we'd be happy to help you. We have those accessible and can send you a link.
Okay, and then can you clarify on something with the LEA software? Can that perform the AI and machine learning analysis, and how do people kind of use that in tandem?
Yeah, our software doesn't directly allow you to do the analysis for the machine learning and artificial intelligence there. But what we're able to do is to provide the structured data as Excel or CSV files from either PolyView or from LEA analysis. Most people, it seems these days, are using open source software programs such as Python or R Studio to perform the data analysis and the visualizations. These programs have a strong user base and community, and they've been pretty widely adopted. So.
And a somewhat related question, can you connect several junior platforms to just one database? Or is it, yeah, that's the question.
Yes, absolutely. You can connect an unlimited number of platforms, junior platforms or big Kahuna platforms or combinations of those to a database. You can collect or connect a variety of third-party integrated analytic instruments, X-rays, Raman instruments, GPCs, GCs, LCs, LC mass specs, so the data all goes into the database. We have customers who have multiple research sites all over the world where data goes into a single database from many different instruments. So it's available to all the researchers in your organization.
Okay. And then after you complete a set of reactions, are there preferred methods to analyze the results to find the hits? So like HPLC, and I think you maybe just answered this, but do other instruments need to be physically connected to the robots for immediate analysis?
Yeah, there are a couple of ways to approach this really. Generally, because you're going to, in reaction screening, you're going to be running hundreds or thousands of experiments. You want a analysis method that's fairly quick. Fortunately, nowadays, there are pretty robust methods for UPLC or UPLC mass spec that can provide sample-to-sample analysis time of only a minute or two, which makes analysis of large collections of experiments pretty simple or straightforward. Depending on the particular technique or the particular field you're in, if you're looking at polymers, you might need GPC analysis, for example, or something else.
Okay. And Rick, I know you know a lot of and see a lot of our customers specifically, but so are most customers treating this as a walk-up instrument, or for the chemists in labs, sort of they have dedicated operators?
Yeah, most laboratories have someone who's a super user of the systems, just so they have a consistent person in the laboratory who can help train others, help facilitate use of the instrument there. A lot of the smaller junior platforms are really walk-up friendly to do things like powder dispensing or reaction screening, so a minimal amount of training to create a design, and users are able to come in and run those workflows. Some of the larger, more complex workflows where we might actually connect multiple big kahuna platforms together tend to be a lot more complicated to run, and those benefit more from having sort of dedicated users or super users at least to help facilitate the utility of them.
Okay, and another question you asked about, I think briefly mentioned powder dispense, and can you explain a little bit more how that works and what the kind of dispense amount range people would expect to have?
Sure. So we have two different powder dispensing capabilities, what we call classic and SV or storage vial technologies. Classic hoppers are larger stainless steel hoppers from a 10 milliliter to 100 milliliters in size. The SVs stand for storage vials, and they use a disposable 4 milliliter glass vial for powder dispensing. With both of these technologies, we have a lot of information, both generated in-house and from customers that, dispensing on the larger end up to tens or hundreds of grams of material is possible. On the lower end, we have a lot of data about catalysts and ligands and materials that show that sub-milligram dispensing down as low as 0.3, 0.4 milligrams of material is quite possible. And if you're want to reach out to us again at unchainedlabs.com on the contact page, we'd be happy to share some of the specific dispense data for catalysts or ligands or the types of materials that you're interested in. We also have videos of powder dispensing that we can share as well.
Thanks, Rick. I think one last question, it looks like. So do you think the software will ever be able to implement AI and machine learning to make its own screen designs based on the results of a previous screen?
Oh, I'd love to see that.
More broad like the question, right? Which is like, is this possible? Are people really going to ever be able to do this, regardless of whether or not it's just us?
Yeah, I think, people are definitely going to be able to do this. It's probably in the short term going to be some sort of a combination of the ability to create designs in some other piece of software, which would then get imported into Library Studio or run directly on Automation Studio. Yeah, some of the algorithms for doing the machine learning things are pretty complex.
Okay, I think that's it for today. So thanks for answering all the questions, Rick, and thanks again for that great presentation. So I'd also like to thank our audience for attending and joining us live today. If you want to have a deeper conversation with our team, so please get in touch with your local account manager. If you don't know your local account manager, you can use info@unchainedlabs.com to contact us. So everyone who registered today will get a link to the recording within a few days. And so thank you again for attending our virtual seminar, and we hope you have a great rest of your day.